you guys know, the centroid doesn't have to be actually in the shape, right? If you calculate something like the centroid of an annulus. What's an annulus? One of these deals, right? If that's a planar region, the centroid would still be in the center, even though that's outside of the actual object. So centroids do not actually have to be in the physical objects, right? They can be out. The balance point for an object can be outside it. Principle of many stupid magic tricks. But anyway. Okay, so we got that done. Well, I got it done. You may not have it done yet. I don't know. Let me try to set up a more interesting polar integral here. I don't want to calculate this one. I just want to set it up, okay? Let's look at the region. Suppose we're looking at r is equal to 6 sine theta and something else that I'll add in a second, okay? First of all, what is r equal? We want to look at this and this bound, some region r, calculate the area of r, right? Now, strictly speaking, you did some of these problems in calculus too, right? Right? Yes, you did. But they appear again here. I guess to make it more interesting, instead of area r, I'll say calculate the integral over r of, I don't know, y over x plus x squared. Ooh. dA. That's probably bad because x will be 0 somewhere in the thing I'm looking at. Let's just say xy plus x squared. There we go. That's exciting. That we would not have asked you in calculus 2. Because in calculus 2, we just asked you to calculate areas of regions using polar coordinates. We've stepped it up a notch. Now we're asking you to calculate the integral of functions over an area. All right, anyway. So what does r equals 6 sine theta look like? That's what I want to talk about. The way I understand something like this is to multiply by r, right? And then, I don't know, x squared plus y squared is equal to 6y, right? So x squared plus y squared minus 6y is equal to 0. So x squared plus y minus 3 quantity squared is equal to 9, completing the square. At which point I learn, aha! R equals to 6 sine theta is actually a circle centered at 0, 3 with radius 3. So, in fact, if I was to draw it, it's something like this, right? That was supposed to be a circle. Anyway, you got the idea. I want to bound that, I want to bound a region by that in some interesting way. So let's also look at, I don't know, r is equal to, let's say, r equals to 3. Why make life difficult? R equals to 3 is interesting enough. So r equals to 3 looks like what? Like that, right? So what's the region which is bounded by both of these? This is the r right in here. Right? So when we think about that region, if you don't mind, I'm going to erase my shading. When we think about this region, and we want to set up the integral in terms of polar coordinates, how do we do it? Maybe actually make that bigger. Ah. Horrible. Not much better. Well, anyway, I'm trying. So we're looking in here, right? Here's the origin. So when you're thinking about setting up polar bounds, you have to ask yourself the question, what's the inside radius, what's the outside radius? How do you figure out inside and outside radius for points? Well, if I start anywhere between this and right up here, there's something special that happens at that theta 1, right? And this point of intersection is also special, theta 2, right? But for 0 less than or equal to theta less than or equal to theta 1, we have 0 is less than or equal to r is less than or equal to what? What's my outside radius? If I just draw it in here so you can see it. I hit this point, right? What is that? That's r equals to 6 sine theta, right? And likewise, for theta 2 less than or equal to theta less than or equal to pi, we have 0 less than or equal to r less than or equal to 6 sine theta. All right? Because, again, that's my radius. But look what happens when you go from the origin out in your shape. On the top, what happens? See, so for theta 1 less than or equal to theta less than or equal to theta 2, we have 0 less than or equal to r less than or equal to 3, right? So when you're calculating this integral in polar coordinates, you have to break it up into 3 cases, really. Now, perhaps you can use symmetry, but I think that my integrand casts a long shadow over using symmetry. So to be safe, I think I wouldn't do symmetry here, unless I could really convince myself. I'd have to really stop and think about using symmetry here, honestly, guys. Maybe there might still be some use for it, but I'm just going to shy away from it. So r xy plus x squared dA. Okay, so what would I have to do? The integral from 0 to theta 1. And then what's my r? R goes from 0 to 6 sine theta. My xy is r squared cosine theta sine theta plus r squared cosine squared theta. My dA is r d theta. Then I do plus the integral from theta 1 to theta 2, the integral from 0 to 3 of r squared cosine theta sine theta plus r squared cosine squared theta r dr d theta plus the integral from theta 2 to pi, integral from 0 to 6 sine theta of r squared cosine theta sine theta plus r squared cosine squared theta r dr d theta. And that, folks, is how you'd actually have to calculate this. Right? So for polar, for a double integral where you're trying to convert bounds to polar, it's important to identify what's your inner radius and what's your outer radius when you're setting up the integrand. There's one other kind of example I'd like to talk to you about, and sadly we have no time. But the thing I was going to tell you is the other one that kind of I haven't covered yet, so maybe I'll put a daily quiz problem on it. You could have something like this in xy space. If your region is like some kind of like slanted, if it's got 4 sides and they're all straight sides, what's that called? Quadrilateral or, okay, quadrilateral. If you have a quadrilateral, you can make a linear change of coordinates. You can make a linear change of coordinates to reformulate it so that in its image, it's just something nice. It's just like nice straight up rectangle. So this would be over in the UV space. So that's another pretty common problem type. We should actually work through one together. So I'll probably put a daily quiz problem on that tomorrow. But the rest of the, so once we get past the daily quiz problem tomorrow, the rest of the time I'm just saving to talk about mission, what are we on? 6? 6, okay. Someone talked me into 7 earlier. Tricksy people, or yesterday. Anyway, so there's that. Anyway, well, have a good rest of the day. I mean, the rest of your day is just going to be downhill from here, really. It's the highlight of your day.